Hi, and welcome to your next lesson in the Waves unit. My name is Mrs. McGee and I'm one of the science directors, and today we are going to be learning about something called refraction. Now, refraction is the effect that actually allows you to do something like what you see in the picture here. This is called crystal ball photography, and it's a really cool effect where you place a glass ball in front of an object and you can see that that object that is being reversed in the glass ball, and you can take really beautiful photos like this one. So before we continue, just a reminder that it's a good idea to try and avoid distractions if you can. So if you're not using your phone to watch this lesson, then put your phone away. But if you are using your phone to watch this lesson, then at least turn the notifications off. For this lesson, you will need a pen and paper and a pen of a different colour, red pen if you have one, if not, any colour will do. So today's starter is going to be a little bit different to some of the recall starters that you've been doing. I'm going to show you a short video which has got a series of optical illusions, little visual magic tricks. And what I would like you to do is have a think about how do you think that these are happening? What are the processes behind it? What does it link to what you might already know about light and how it travels and how we see? So the first one, you start with a glass of water up against some arrows that have been drawn on a piece of paper. Move the glass away from the paper and look what happens. You could also try this with different patterns in the background. Just move the glass of water in front of them. What do you think is going on here? Why don't you give this a go at home and do different patterns on a sheet of paper, different colours, different drawings, and see what they look like when you move a glass of water in front of them. Or you could try putting something into the glass of water. So for example here, we've put a pencil into a full glass of water. Have a look at that. So what is going on here? So in the first part of today's lesson, you are going to learn how to describe what refraction is and explain why it occurs. And then in the second part of the lesson, you're going to learn how to construct something called ray diagrams to show refraction actually happening. Now in the starter activity, you saw lots of different types of optical illusions, but the reason why we see objects is because light travels from those objects into our eyes. This visible light, however, is only one of 7 different categories of waves that form part of the electromagnetic spectrum. So I'd like us to do a quick knowledge retrieval task. You've done the lesson on the EM spectrum, so the electromagnetic waves. And what I'd like you to do now is try and remember what the names are of the different electromagnetic waves. And there are 7 of them that you need to recall from the previous lesson. I'm going to give you 60 seconds to do this. Get your pen and paper and write them all down. If you can, try and put them in order from the longest wavelength to the shortest wavelength. So I've put a diagram here to help you with that. So on the left-hand side, you should have your waves that have the longest wavelength, and you can see that you carry on down the spectrum to the right-hand side where you have your waves that have the shortest wavelength. So can you list for me the 7 different electromagnetic waves in order? Off you go. Okay, let's see how you did. Grab your red pens and tick off the ones that you got right. So the first wave in the EM spectrum, which has the longest wavelength, is radio waves. Then it's microwaves, infrared, visible light, so this is the light that we see, ultraviolet, X-rays, and gamma rays. So give yourselves a mark out of 7 for listing the electromagnetic waves. Let's now have a think about what was happening during those optical illusions that you saw at the start. So here we've got the last trick that you saw where you place a pencil in a glass of water and it looks like the pencil is split in two. It looks like the pencil has this break in the middle of it. Now, is the pencil actually broken? No, of course it's not. All you've done is you've put it into the water. So what is actually happening here? Something is happening to the light as it leaves the water and travels to our eyes, because the way that we see objects, as we said earlier on, is when light reflects off those objects and goes into our eyes, so we see the object. So the part of the pencil that is in the water, the light traveling from that, something is happening when that light goes out of the water, through the glass, into the air, and then into our eyes. Here is another optical illusion that is going to help us understand what is happening here. Have a look at this. If you start with a coin placed in a bowl of water and then move back until you're in a position where you can no longer see the coin, you then take some water and slowly pour it into the bowl. And what you start to see is the coin. Now, I promise you that the water has not made the coin move. And if you don't believe me, try this yourselves and use blue tack to stick the coin to the bottom of the bowl. But by adding the water into the bowl, something has happened to the light coming from the coin that means that we can now see the coin, even though the coin has not moved and our head, our eyes, have not changed position either. So let's see if we can explain what is happening here. So if you have a coin in a beaker and you position yourself so that you cannot see that coin in the beaker, in the bottom of the beaker, the reason why this is happening is because no light from the coin can actually reach your eye. So if I show you with this blue arrow here, this is the light that is reflecting off of the coin, and you can see that it cannot reach your eye because of the position that you are in. So the light travels in a straight line and cannot bend around the edge of the beaker in order to reach your eye. So you can't see the coin. Now, what happens when we add water into this beaker? Well, look at what is happening to the light now. The light coming from the coin travels in a straight line through the water, but then when it moves from the water into the air, it bends slightly. It changes direction. And because it changes direction and then continues in a straight line, it can reach your eye. This is what refraction is. So refraction is when light changes direction when it moves from one substance into another, and we call these substances media or a medium. So the water is a medium that the light can travel through, and then the air is another medium that the light can travel through. So when the light goes from the medium of water into the medium of air, it changes direction. The reason why this happens is because there is a difference in density between the water in the beaker and the air. So water is more dense and the air is less dense than the water. Now remember, when I talk about density, I'm talking about how packed together the particles are in a given volume. So this could be a way to represent the density of water. All the water particles are tightly packed together in that volume. The air is less dense. This means that the particles are more spread out in the same volume. Okay, so when light travels from a more dense to a less dense medium, it will change direction. The same will happen if the light travels from the less dense to the more dense medium. Again, it will change direction. So if I give you a definition now of refraction, refraction is the change of direction of light as it passes from one medium to another medium with a different density. Now, if you're a higher student, you also need to know that the change in density actually changes the velocity of the light. And it's because of this change in velocity, this change in speed, that the light actually changes direction. You can actually investigate refraction really easily in the science lab using just two pieces of equipment. The first is a ray box. So this is a lamp essentially, so a source of light, but what we've got at the front of it is just a very thin slit. That means that instead of getting lots of light out of the lamp, we are just getting a nice thin line of light, which we call a ray. And the second piece of equipment is a glass block. Now we're using a glass block here, but you could use blocks made of other items such as plastic, as long as they are transparent and they allow the light to go through. You could also do this with water in a beaker, for example. So we place the glass block in front of the ray and at an angle so that you can see the light is going through the block, not dead on, not perpendicular, but at an angle. And I'm going to start by tracing around the block, just so that when I remove it, I have the shape of it on the piece of paper. And now I want to draw where the lines of light are, the light rays are, but I can't get in there easily with a ruler because of all the equipment in the way. So I'm just going to draw two X's along the ray of light that I can then use as a guide to draw the rays. So now I've removed the block and I get my ruler and I'm going to carefully join up the two crosses that I drew all the way to the boundary with the glass block on both sides, and that shows where the light was travelling through the air before it went into the block and then again after it came out of the block. So here is the diagram that I drew using the ray box as a source of light and the glass block. So I'm just going to label this very quickly so that we know what each medium was. So that block was made of glass, and then outside the block, the medium is obviously air. And I'm going to add arrows to the lines that I drew just to show the direction that the light is moving in, so it's really clear which direction the light is going. Now I've drawn the two rays on either side of the glass block, but what I haven't yet drawn is the light that went through the glass block, because obviously you can't do that when you've got a glass block in your way. So now that I've moved that out of the way, what I can do is I can just join up the two rays of light like this using a ruler and a pencil, and that shows the path that the light took as it passed through the glass block. So you can see really clearly that at this boundary here on the left, the light changed direction when it moved from the air into the glass. And then here at this boundary on the right, again, when the light moved from the glass back into the air, again, it changed direction. And this is happening because the glass is more dense than the air around it. Therefore, as the light goes into the glass and then out again, it changes speed, which makes it change direction. One way to try and understand this is to think about this model of a car travelling along a road that you can see here. So if the car travels along a road and hits a patch of sand, then it will change direction because the first wheel that hits the sand is going to slow down, and this will cause the car to actually turn slightly before it then carries on moving through the sand. So the same thing is happening with the light. When it moves from one medium to another, because of a slight change in speed, it will change direction. So the light moving through the air moves in a straight line. When it crosses that boundary between the air and the glass block, it will change direction slightly because of the change in speed. And then when it moves out of the block and back into the air, again it will change direction. So let's do a quick progress check to see how much you've understood of that. What I would like you to do, in your own words, is to describe what refraction is and why it happens. Now, if you wrote down the definition that I gave you earlier on, I'd like you to cover that up with your hand and just have a go at writing it again in your own words. To help you, I've got these keywords here that you can use. You don't have to use all of them, but if you can use all of them, then that will make your description much better. And if you're a higher tier student, then you need to try and use that last word, which is in purple there, velocity. I'm going to give you 2 minutes to do this on your own. Off you go. Okay, let's see how you got on. I'd like you to get your different coloured pen now, and I'm going to show you one example of what you could have written. Now, you don't need to have written exactly what I have written here, but every time you have used one of the keywords in the box, I'd like you to give yourselves a tick. So refraction is when light changes direction as it moves from one medium to another. This happens at the boundary between the two media if one is more dense than the other. So for each of the keywords that you used, give yourself a tick. Now, if you're a higher tier student, you could also have added the following: that the change in density changes the velocity at which the light or the EM wave travels. So the light changes direction slightly. That you need to improve your description, then have a go at rewriting it using the model that I have given you here. Pause the video and then start again when you're ready to move on. Well done for finishing that first part of the lesson. You should now be able to describe what refraction is and explain why it occurs. In the second part of this lesson now, we're going to look at how to construct what we call ray diagrams to show refraction happening. We're now going to look at the different parts that we would label on this ray diagram. So we're going to focus on the left-hand boundary here first. So where we have the light entering the glass block, we can draw a line perpendicular, and that's why I'm using a protractor here. We can draw a line that is perpendicular to the boundary that the light is passing through. Now this is an imaginary line, and I'm drawing it in dashes rather than a solid line to show that it's not actually a physical line. But this line here is called the normal. So the normal is an imaginary line that is perpendicular to the boundary that the light is passing through at the point at which the ray passes through it. Now, the ray of light that comes to the boundary, so the first one here, is called the incident ray. And then the ray of light that comes out when the light has been refracted is called the refracted ray. And we can also then label two angles. So the angle between the incident ray and the normal is the angle of incidence. So I'm going to just label that I, and I'll write the label down here. So I is the angle of incidence. And then the angle between the refracted ray and the normal is called the angle of refraction. So I'm going to label that R. So R is the angle of refraction. So the key thing to look at is what happens to the refracted ray when the light is actually refracted at this boundary. So you need to understand whether the refracted ray moves towards the normal or away from the normal. So if we look at this one that I've already labeled here, the incident ray comes at the boundary at this angle, and when the light moves into the glass block, you can see that the refracted ray moves slightly towards the normal, and that's because the light is moving from the air, which is less dense, into the glass, which is more dense. If we look at the other side of the glass block here, so again I'm going to draw using dashed lines the normal, so it's perpendicular to the boundary. And in this case, my line coming in, the ray coming into the boundary here, so in this direction, this is now my incident ray. And then the ray coming out on the other side is my refracted ray. And then my angle of incidence is the angle between the normal and the incident ray, so that's there. And my angle of refraction is the angle between the refracted ray and the normal there. And so now if you look at this case, where the light is going from the glass, which is more dense, back into the air, which is less dense, you can see that the light, the refracted ray, is moving away from the normal. So it's come in at this angle here, and then when it's passed from the glass to the air, it has moved away from the normal and then carried on in a straight line. So we're now going to practice drawing lots of ray diagrams together, but first it's important to know the different names of the different sections of this diagram. So what I'd like you to do is sketch the diagram that's here. I'd like you to pause the video whilst you do this, and then when you've sketched it, come back and we will label the diagram together. Okay, so let's have a look at the labels. So number 1 is our glass block. Number 2 is the incident ray. Number 3 is the refracted ray, so that is the ray of light that has changed direction when it's entered the glass block. Number 4 is the normal, so that is the line that is perpendicular to the boundary that the light crosses, so that boundary between the air and the glass. Number 5 is the angle of incidence. So the angle of incidence is this angle between the incident ray and the normal. And then number 6 is called the angle of refraction. So that is the angle between the refracted ray and the normal. Have a go at adding these labels to your diagram. Okay, so I'm now going to show you again step by step how to draw a ray diagram for refraction, and then you're going to have a go at this yourself. So let's say that we want to show refraction of light as it travels from air into glass. The first thing that you do is to draw the incident ray through the air, which is the first medium. So a straight line using your ruler and pencil, and don't forget to add an arrow to show the direction that the light is traveling in. Next, you draw the normal line. So it's best to do this as a dotted line, and you draw it at right angles to the edge of the medium. So that's the boundary where the incident ray hits the edge and where it travels from one medium into another. Then you need to decide whether the refracted ray is going to bend towards or away from the normal. Now at this point, it's useful to recall the model that I showed you earlier on of the car traveling along a road and then hitting the sand. If the car is traveling from the road into the sand, it is going to slow down slightly and it will turn towards the normal. So here the ray is going to be refracted and turn towards the normal when it moves from air into glass. So then you draw the refracted ray, and again use your ruler because it's a straight line, and make sure to add the arrow to show the direction that the light is traveling in. Okay, so I'd like you to try drawing ray diagrams by yourselves now. There are 3 diagrams here. I'd like you to copy these down and then complete them by adding the normal and then the refracted ray to each diagram. I'm going to give you 2 minutes to do this. Off you go. Okay, let's see how you did. So in the first diagram, when you draw the normal, you're drawing a dotted line perpendicular to the boundary between the air and the glass. And now you need to decide, is the refracted ray going to move towards the normal or away from the normal? So air is less dense than the glass, which means that when the light goes into the glass, it is going to slow down slightly. So think about that car moving from the road into the sandbox, and it is going to turn towards the normal. Now don't forget when you're drawing your refracted ray to add your arrows to show the direction. Let's look at the second diagram. So again, our normal is perpendicular to the boundary between the glass and the air. Now this time the light is traveling from the glass, which is more dense, into the air, which is less dense. So it's going to speed up slightly as it leaves the glass, which means it will turn away from the normal. And then in the third diagram, we've got the light traveling from the air into water. So which one's more dense? Well, the water is more dense. Let's add our normal line there. So the water is more dense. Therefore, the light is going to slow down slightly as it goes into the water, and it is going to turn towards the normal. Okay, so now that we've been through those three, have another go at these two. So again, copy the diagram and complete it by drawing the normal and then deciding whether the refracted ray is going to move towards or away from the normal and adding in the refracted ray. The second diagram is a little bit more complicated, but I'd like you to give it a go anyway. I'm going to give you 1 minute. Off you go. Okay, let's see how you got on with these ones. Now with the first diagram, the normal here is vertical, so perpendicular to the boundary between the air and water. And this time the light is moving from water into the air. So water is more dense, the air is less dense, so the light will speed up slightly, which means it will move away from the normal. And then in the last diagram here, so slightly more complicated because the boundary is actually curved, but you just need to focus in on the point where the light hits the boundary. So our normal, we are going to draw horizontally there, so perpendicular to an imaginary tangent at that point where the light hits the boundary. Now the light is moving from glass into air, so it's going from a more dense to a less dense medium. So again, it is going to move away from the normal as it crosses that boundary. So well done for giving that a go. In this first part of the lesson then, we described what refraction was and explained why it occurred. And in the second part of the lesson, we've been practicing constructing ray diagrams to show how refraction happens. If you want more practice, then there is a Google Doc that is included with this lesson that has more ray diagrams that you could copy and complete, or print the Google Doc off and complete the ray diagram straight onto it. Here are the key learning points from today's lesson. If you would like to add these to your notes, pause the video now. Now, if you are a foundation student, this is where the lesson ends for you. So I'd like you to go and complete the Google quiz attached with this lesson. However, if you're a higher student, you need to keep watching because there is one more thing that you need to learn about. So as a higher tier student, you need to be able to explain that refraction of electromagnetic waves is due to the difference in velocity of waves in different substances. But you also need to be able to use wavefront diagrams to illustrate this happening. During this part of the lesson, if you need to pause at any point to make notes, please do, because it's worth thinking about this carefully and really trying to understand what is happening with the waves here. Okay, so here we have an animation to show refraction, and the white medium at the top is air and the purple medium at the bottom is glass. So refraction happens because light travels more slowly in denser media. So here the glass is more dense, which means that the light is going to travel more slowly in the glass than in the air. So refraction occurs and the light moves towards the normal when it moves from the air into the glass. And you can see that there is actually a little bit of light that is also reflected at the same time, but we are going to just ignore that bit for this simulation. Now, because light is actually made of waves, it has what we call fronts. So each front is a crest, and we can show these fronts here as straight, parallel, evenly spaced lines that are drawn at right angle to the direction of travel. So if I pause the simulation there, you can see that each of these fronts here is parallel to the next front, and they are drawn at right angles to the direction of travel of the wave. Now, have a look at what happens when the wave is actually refracted at the boundary between the air and the glass. So you can see here that at this point, the wave fronts will also change direction because they need to remain perpendicular to the refracted ray. You will also notice that the distance between each wavefront becomes smaller. So the wavefronts are closer together in the glass than they are in the air. And this shows that the light is actually traveling slower in the glass. So the reason why the light is traveling slower in the denser medium is because there are more atoms in its way. If the light hits the boundary at right angles, so along the normal as shown here, then you will notice that each part of the wavefront slows down at the same time as it moves from the air into the glass. So the wave continues in a straight line, but just more slowly, and the wavefronts are closer together because they have slowed down. But something different happens if the wave hits the boundary at an angle here. So again, just ignore these reflected waves here. So as the wavefront here approaches the glass at an angle, you'll see that for each wavefront, one side of the wavefront hits the glass first. So the part of the wavefront that enters the glass first is going to slow down first. And so if we look at this wavefront here, you can see that one part is already in the glass, therefore moving slower, whereas the top part is still in the air, therefore still moving faster. And this is why the wavefront actually changes direction as it crosses that boundary from the air into the glass. So let's now look at how you would draw these wavefront diagrams. So you can see here an example where light is moving from the air into the glass. Now the easiest way to draw this diagram yourself is to start by drawing the incident ray, the normal, and then the refracted ray, so that you've already decided on the direction of each of the rays. Once you've done that, you can add in the wavefronts. So the air is less dense than glass, so the wavefronts of the light as it travels through the air will be more spaced out. And you can see that as the light goes into the glass, that the wavefronts come closer together because the glass is more dense, and so the light has slowed down. So if you look at wavefronts A and B, they are closer together, but they are still parallel. If you look at wavefront C, you can see that the part of wavefront C that is in the air is still going in the original direction, but then the section of wavefront C that is in the glass has changed direction slightly, and it has bent to follow the refracted ray. And then again, look at wavefront D, and you can see the bend at the boundary between the air and glass. Now remember that when you draw your wavefronts, you need to draw them perpendicular to the light rays. Here's another example, but this time the light is traveling from the glass into the air. So the refracted ray has moved away from the normal because the air is less dense than glass. So again, look very carefully at how the wavefronts have been drawn. They're all parallel to each other and they are perpendicular to the rays of light. But at the boundary, you can see that the wavefronts bend, they turn, they change direction. And in the air, the wavefronts are more spaced apart to show that the light is moving faster than it was in the glass. It would be good practice for you to pause the video now and copy these diagrams to practice drawing these wavefronts. So we're going to do some more practice now. And I'd like you to copy these two diagrams really carefully and suggest what you think a possible medium might be for medium A, medium B, medium C, and medium D. I'm not going to put a timer up for this one because I'd like you to pause the video and work at your own pace. Some of you may be able to draw this diagram quicker and some might take a little bit more time. So pause the video now and work at your own pace to copy the diagrams and suggest what a medium for A, B, C and D might be. Okay, welcome back. So let's have a look at what these media could have been. So in the first diagram on the left hand side, you've got the light travelling from medium B into medium A. And if you look at the distance between the wavefronts, in medium B the wavefronts are close together, but in medium A they're further apart. So this suggests that light travels slower in medium B. Therefore, medium B must be more dense than medium A. So you could, for example, have suggested that medium B is water and medium A is air. It doesn't have to be these exact ones as long as you've suggested a medium B that is more dense than medium A. Now, if we have a look at the right-hand diagram, this time the light is travelling from medium D into medium C. And if you look at the wavefronts, in medium D, the wavefronts are further apart, so the light is travelling faster. And in medium C, the wavefronts are closer together, so the light is travelling slower. So the light is going from a less dense to a more dense medium. So medium D must be less dense. But the difference in density is quite big because you can see there is quite a big difference between the wavefronts, the distance to the wavefronts in medium D and the distance of the wavefronts in medium C. So it could be something like air and glass. So medium D could be air and then medium C could be glass. Again, these are just two examples. You might have come up with a different answer. As long as medium D is less dense than medium C, then that is correct. Okay, this is the last bit of practice for today. So again, I'm not going to give you a timer. I'd like you to pause the video and work at your own pace on this one. I'd like you to copy these three diagrams and for each add the normal, the refracted ray, and then the wavefronts on both the incident and the refracted rays. So pause the video, work at your own pace, and then unpause when you're ready to look at the answers. So let's see how you got on. In the first diagram on the left, our light is moving from water into the air. So we draw the normal perpendicular to the boundary at the point where the light hits this boundary. Then water is more dense than air, so the refracted wave is going to move away from the normal because light is travelling faster in the air. And when you add the wavefronts to the rays, your wavefront should be perpendicular to each ray, and the wavefronts in the water should be closer together because the light is travelling slower, and in the air they are further apart because the light is travelling faster. So if we look at the second diagram now, here's your normal, and because light is travelling from air, which is less dense, into water, which is more dense, it's going to move towards the normal. And then when you add in the wavefronts, they also change direction as the light moves from the air into the water, and the wavefronts in the air are slightly further apart, and in the water they are closer together as the light slows down. And then the final diagram, here's your normal again. Now this time the light is moving from glass into air, so glass is more dense than air, so the light is going to move away from the normal when it travels into the air, and the wavefronts again are going to change direction following the rays, and this time there is a really big difference between the distance between the wavefronts in the glass and in the air, because in the glass the light will travel much slower because glass is much more dense than air, and so in the air the light is going to travel much faster, and so the wavefronts are further apart. Okay, so well done. You've reached the end of that lesson. So now I'd like you to go and complete the Google quiz assigned with this. Remember, it's marked automatically. And if you want more practice with completing ray diagrams, then have a go at the Google Doc that is included or ask your teacher for some more examples. These are some additional notes on drawing wavefront diagrams and explaining why refraction happens.